Welcome back. Hope you had a good lunch and we are so excited to get going with our third keynote of the day, which will be on blockchain-empowered networks for IoT. Now, blockchain technology has led to a significant interest in managing databases in a decentralized way without the security concerns that stem from centralized platforms. Now, in this session, we will explore how we can leverage blockchain for IoT and discuss whether blockchain is suitable for latency-sensitive applications by analyzing the data freshness in the blockchain-enabled monitoring networks. We'll also talk about future challenges of blockchain-enabled networks for IoT. And to address all of this, I'd like to introduce our next speaker from Korea. She received the 2020 Haidong Young Engineering Researcher Award, the 2020 IEEE Communication Society Young Author Best Paper Award, the 2017 IEEE Communication Society AP Outstanding Paper Award, and the 2014 IEEE Communication Society AP Outstanding Young Researcher Award. Ladies and gentlemen, let us welcome from the Department of Information and Communication Engineering, Daegu Gyeongbuk Institute of Science and Technology, Associate Professor Jemin Lee.
Okay, thank you for the kind introduction. Let me share my slides first. It is very nice to see all of you today, and I'm very happy to participate in this event today. Today, I will talk about the blockchain-enabled network for Internet IoT. So this is the outline of today's talk. So I will briefly introduce the blockchain technology and then also discuss about how we can define the blockchain latency and see what kind of blockchain parameters are affecting the latency. Finally, we will see the impact of the blockchain parameters on the monitoring IoT networks. I think all of you heard about the blockchain before because basically the blockchain is the immutable distributed database, which has a sequence of blocks that are linked and replicated on multiple nodes. So as shown in this figure, the blocks are linked in this way. First of all, each block has multiple transactions, and then we can get the value from those transactions. And then also using the hash of the previous block, we generate the new hash values. And these new hash values are used to link the next blocks and so on. So because of this structure, if someone wanted to change certain data in this transaction 1, then it is almost impossible because they need to change all the hashed value of the previous blocks. So that's why, because of this structure, the blockchain can guarantee the data integrity. So when we consider the distributed system, there have been many issues, including the data integrity and consistency issues. This is related to whether the data in this database is the right one, and also which has not, that means actually whether it is not modified at all. And also whether this data is exactly the same as the one in the other distributed servers. To overcome those issues, the blockchain technology can be used. So by using this blockchain technology, we can solve the security concerns since it is impossible to modify the data. And also we can have the transparency for the transaction processing. Also, we have the consensus-based data verification. Blockchain is now used in many applications and services. So I want to introduce certain use cases in here. The first one is the blockchain-based core verification service for bank. This is developed by Samsung SDS and used in Korea for 16 banks now. So until now, the banking customers have to go through all the inconvenient process of the renewing their digital certificates every year for each bank. However, this bank sign manages the certificate information using blockchain and shared with other banks. So we can access the banking service of multiple banks using a very simple verification only. And second one is the Walmart food supply chain, which is developed by IBM. So by placing the supply chain on the blockchain, it allows making the process more transparent and traceable. So people can have more trust on their information, especially for the like origin of certain fruits or meats. They can have more trust on this information. And next one is quite recent one, which is the blockchain-based COVID-19 vaccination verification system. This application is now we are using this application in Korea now. After the vaccination, people can get the certificate from this app using their personal information. And this certificate can be used to get some exemption from social restrictions. So once they show this certificate at a certain restaurant and so on, then they can get in the restaurant with a large number of groups and so on. So although many applications of blockchain exist, when people see or hear about the blockchain, they usually come up with the Bitcoin, which is the digital currency. This Bitcoin and Ethereum, another blockchain system, are the public blockchain. The public blockchain is based on open point-to-point networks. So that means anyone can join or leave these blockchain networks anytime. Because of this anonymous participations, intensive consensus process is required to commit blocks to the chain, such as like mining in Bitcoin. So due to this reason, it takes a very long time for the block commitments. However, there is another type of blockchain, which is a private blockchain. Some examples are Hypertone Fabric and Ripple and so on. This private blockchain is type of blockchain networks where only a single authority or organization has control over the whole network. So for this type, only a lot of people can participate in this network. So they have very strict membership management. So therefore, because of this, complicated consensus process is not required at all. So it becomes more efficient. For example, the processing rate for one transaction, it becomes like 500 times faster in private one compared to the public blockchain one. So, when the company, they wanted to use this blockchain technology for their service and applications, they usually wanted to safeguard their sensitive information. So they generally use the private blockchain. So the previous use case one that I introduced before is also based on this private blockchain. So I also focus on this blockchain, private blockchain as well, and then use this Hypertone Fabric. Among the private blockchain systems, one of the most popular one is this Hypertone Fabric. Hyperledger is an umbrella project of open source blockchains and started by Linux Foundation in 2015. And now many companies are participating in contributing to this project, including IBM and Intel and so on. So they provide the modular architecture with a smart contract execution and configurable consensus and membership services. And also we can download the code for the implementation of Hypertone Fabric in the following links. So we also use this code from this website for the implementation, and we'll talk about more details later. I will now describe how the generated transactions become the blocks and commit to the ledger in Hypertone Fabric. This is about the transaction flow. First of all, in the Hypertone Fabric networks, there are multiple nodes, like a client which generates the transactions, and then endorsing peers and ordering peers and committing peers that has the ledger. So I will describe the whole process that of the transaction flow in 3 phases. The first phase is the endorsing phase. So the clients, they generate the transaction proposal and send it to the endorser. Then this endorsing peer endorser check whether this proposal is okay. Basically, they check whether this proposal requests a certain change in the current version, not the old version, and so on. So if this proposal is okay, endorsing peers give the endorsement. If the client receives the endorsement from multiple endorsers enough, then they transmit this transaction to the ordering peers. Then in the ordering phase, the endorser endorsed transactions is ordered chronologically. Then the ordering period generate a block that contains multiple transactions. Here, there are 2 important parameters affecting this ordering service. First is the block size. This is a maximum number of transactions in a block. And another one is the block generation timeout. For example, if the block size is 10 and timeout is 2 seconds, when the number of transactions in a block become 10, within 2 seconds, it become a block. When the block is now fully filled within 2 seconds, I mean within the timeout, then the block is also just generated after the timeout. So like this, those 2 parameters are affecting the latency of this ordering phase. We will discuss it later again. And the last phase is validation phase. So each peers with the ledger receive the generated block from ordering peers and verify whether this transition in the blocks are correct ones. Many, they do the verification system chain code to investigate whether the endorsement in each transaction is valid. Secondly, they do the multi-version concurrency check. This is mainly to check that whether this version of the key captured during the endorsing phase is the same as the current version in the ledger. So if some transactions do not pass those validation, they become invalid and do not update the ledger. Then let me talk about the challenges in utilizing the Hypertone Fabric. As talked before, the blockchain has many benefits, especially in the aspect of security. However, there are some costs we need to pay, which is the additional latency. So I believe this latency can be a main drawback in the utilization of the Hypertone Fabric, especially when we use this blockchain for real-time or latency critical applications and services. Hence, in the following slides, I would like to discuss about this blockchain latency. Specifically, I would like to answer those 3 questions like how long the blockchain latency will be, and how do the Hypertone Fabric parameter affect the latency, and then how we need to design the blockchain-enabled network. So next part is to answer the first question, how long the blockchain latency will be. So this part is based on our recent paper, which is uploaded in archive now. So you can find more details, more information easily in this link. So now, let me define the latency in Hypertone Fabric networks. We have defined 3 phases for transition flow before. We have now defined the latencies for those 3 phases. First is the endorsing phase, so which is the time taken from the transaction generation at the client until getting the endorsement from the endorsing peers. And the second one is the ordering latency. This is the time taken from the time that a transaction enters an ordering service and until it gets out as a block. And the last one is the validation latency, which is a time taken to validate and to commit this new block to the ledger. So all transitions in the same block are validated sequentially, but they are committed to the ledger or together as a batch. So all the transitions in the same block have the same validation latency. So the total latency will be the time taken to process all those phases, and we define this latency as the ledger commitment latency here. So to design the blockchain-enabled networks, we need to know about those latencies. For that, we can measure them by implementing the Hypertone Fabric, but also it is important to analyze the characteristics of those latencies. This is what we have done in this work. To measure the latencies, we first implement the Hypertone Fabric version 1.3 here in the machine with those specs. Also, we use the Kafka zookeeper-based ordering service and consider one endorsing peer and two committing peers and so on. We measure the latency with changing Hypertone Fabric parameters, including the transaction generation rate at the client's block size and block generation timeout. This is the measurement result. Based on the measured latencies, we plot the histogram first, which is the blue bars here. So we then, based on this shape of the histogram, we then find the probabilistic distribution which match well with this histogram. So we found that for inducing latency, the exponential distribution match well. For the validation latency, the GEV gives the best fit. And for the endorsing ordering latency and total latency, we found that the gamma distribution fits very well. Regarding the total latency, the best fit distribution is the gamma distribution, so which has the PDF in this form. They have alpha and beta here, which are the shape and the rate parameters. So based on this histogram, we found, based on the histogram that we obtained before, we found the alpha and beta that gives the best fit to those histograms. So you can see here that even we change the transaction generation rate from 8 to 11, the gamma distribution fits well. To check whether it does really fit well or not, we have also done the KS test. So KS test is a statistical test that evaluates the goodness of the fit. So usually the test returns the KS statistic values, and if this value is smaller than critical value, which is 0.05 in our setting, we can pass the test. So as you can see in this table, we can see that for all cases, the KS statistic value were less than the critical value. So that means they all passed the test. We also plot the CDF of the total latency. So as you can see here, although they are not exactly the same, but they are very similar to each other. So for different settings, such as different values of timeout and block size and transition generation rates, we also provide the alpha and beta that gives the best fit. You can find more information about this kind of data in our paper. So we expect that people can use those results for their own research without having the difficulty in implementing the Hypertone Fabric. However, I also need to mention that this fitting not always works well. For certain cases, we cannot find any distribution matches well. So we also investigate what those cases are and found two cases that does not have any best fit distribution. The first case is the timeout dominant block generation environment. For example, when the transaction generates very slowly, then blocks are hardly filled out within the timeout. Then most of the new blocks are generated by timeout. So in this case, the ordering latency becomes equal to the time of the ordering latency become equal to the timeout for a large portion of the transitions. So this is why we have some peaks in the histogram like here and here. And in this case, they does not have any similar probabilistic distribution. And the second case is the block size dominant block generation environment. For example, when the transaction generated very fast, then most of the new blocks are generated with the maximum size before the timeout expires. So in that case, the blocks are generated very fast, which gives a large load at the validation phase. So each block needs to wait very long time at the validation phase, which provides this long tail in this histogram like this. So this case also does not have any similar probabilistic distribution. So for those cases, the fitting doesn't work well. But however, I think those cases are the ones that have very unreliable Hypertone Fabric setting, so that we might not have in real applications or service. Then now let's see what kind of blockchain parameters affect the latency. This part is also based on our paper, which is published in this year. So you can find more information in this paper. So for this part, we have shown the effect of those key Hypertone Fabric parameters. When the transactions is generated at the IoT device, we need to go to the Hypertone Fabric networks. Networks. So that's why we also need to consider this successive transaction probability as a key parameter in Hypertone Fabric. So not only with the block size or timeout or transition generation rate, you also consider this successful transition probability. So because the generated transaction, when they reach the Hypertone Fabric network, the communication can be unstable or fail. So it might not arrive at the Hypertone Fabric network successfully. So this probability is to show that the probability that the transaction is successfully delivered to the Hypertone Fabric network. And also, we also need to see the impact of the number of endorsing and ordering periods, which is related to the Hypertone Fabric network design issue. So based on, so first we see the impact of block size and block generation timeout. So here, x-axis are block size and block generation timeout. And you can see the red curve in those graphs, red curve showing the blockchain latency. So here, we need to first know that as the block size and timeout increase, the block generation rate decrease. Because block size, when the block size is smaller, then block will fill out very fast, and timeout is smaller, then they also generate the block very fast. So based on this understanding, for when the block size and block generation timeout are small, the blocks are generated very fast. So it gives long latency in the validation phase. So the latency can decrease as the block generation rate decrease. However, after some value of the block size and timeout, the total latency increases because this is because the ordering latency increases as the block size and the timeout increases. So it is important to set up the block size and timeout properly and carefully to lower the latency. Next, we see the impact of transaction generation rate as well. So as the transaction generation rate of the certain key value increases, we can have a frequent update on the target key value. But this can cause the MBCC verification failure because the version they used in the endorsing phase can be changed before they commit to the ledger. So then they become the invalid. So the total latency increases as the transaction generation rate increases. The next one is the impact of the successful transmission probability. So as the successful transmission probability increases, the latency decreases first because the higher transitional arrival makes the block generation faster. However, after a certain point, this higher transitional label gives higher load at the Hypertone Fabric networks, so the latency increases. We also see the impact of ordering and indexing nodes. So here, the ordering nodes is K here, and the indexing node is E here. As we increase the ordering nodes or indexing nodes, we can see that the latency increases. So, but actually, if we have a more ordering nodes and more indexing nodes, the Hypertone Fabric networks become more reliable. So there is also some trade-off between the latency and the system reliability in Hypertone Fabric networks. As a last part, we will see the impact of blockchain latency on monitoring networks. So this part is also related to our recent paper, which is uploaded in archive now. So you can find more information in this paper as well. Blockchain-enabled IoT networks can be shown like this figure. So each IoT device transmits transactions to the Hypertone Fabric networks, and all the data are managed in the ledger. As a one example, what we are going to see here is the blockchain-enabled monitoring networks. Here, each sources and sensors distributed in the network, they sense the information of its surrounding area and generate the packet and with the observed information. And this packet is transmitted to the nearest base station and delivered to the Hypertone Fabric by this base station. The packet is then in this network, there can be two types of latencies. The time first is the transmission latency. This is the time taken to transmit this packet to the base station. And also we will have a ledger commitment latency because these packets need to be processed in the Hypertone Fabric network to commit to the ledger. Here we consider the age of information to see the impact of blockchain latency. This is this age of information is the elapsed time since the information was generated. So that's why the age is used here. So when the sensor measures something like 5 minutes ago, then the measured information have the age of 5 minutes now. So this age of information is also related to the accuracy of the information because all the information usually gives different information to the current one. So this is actually quite important measurement in machine learning as well, since all the information can give the long decision in machine learning applications. So in the sensor network, in the database, they receive the data and update the information. So the age of information in this database can be seen as the AY path like here. So for example, when we have the updated data at this point, TU1, then the age of the information drops, and then the age become increase linearly as time goes, and then they drop again when they have another updates of the information. So we use this age of path to measure this AY related performance, such as the AY violation probability here. So AY violation probability is the probability that the AY is being larger than this target AY. This is actually due to the target accuracy that we wanted to have. So this probability shows the portion of time that we have less accuracy than target accuracy for certain information. In the blockchain-enabled network, we also need to consider the MVCC verification carefully because actually not all the transactions update the information in this network. Only the ones past the validation can update the information of the ledger. For example, let's say the packet is generated at this point, GK-1 for the version 1, and they transmit this packet to the Hypertone Fabric, and they arrive at this point, K-1, and they do all the processing to commit to the ledger. And then after this point, at a certain time, this UK1, they can update this packet related information, and the version will be changed to the version 2. However, before this update happened, they can also generate another packet at the sensor. And at this point, they can also generate for the change of the version 1. However, when they arrive at the Hypertone Fabric, the version is already changed to the version 2, so this packet can be invalid. So when we consider this age of information and so on, we only need to consider the packets that gives the valid updates. So that's why we call it as the effective packets in this work. So all the details about the AUI performance and then mathematical analysis, you can also find more information in this paper. So here we simply see the impact of network parameters in this age of information aspect. First, we can see that as the block size increase and timeout increase, as we can see before, the AY also decrease first and increase later. So this is also related to the validation latency and order latency and so on. And so here we can see that there exists the optimal block size and optimal timeout that provide the best performance in terms of AOI and AOI violation probability. So those optimal values can be changed according to the different network setup. So here, this optimal value, so based on this result, we can set up this optimal block size and timeout according to their own network setup. And also, we see the impact of target successful transmission probability as well. So having higher successful transmission probability means communication environment is reliable. And usually in the wireless network, having higher successful transmission probability means is always good, because always good. However, in this blockchain-enabled network, this higher successive transmission probability is not always good, as we can see, as you've shown it before. So this is why the AOI decrease first and increase as the successive transmission probability increases. So when we design the blockchain-enabled network, we need to carefully consider the blockchain latency because the design need to be changed according to the blockchain parameters and the communication parameters, which is different to the conventional networks. So as a summary, in this talk, I just focus on the latency in the blockchain networks, which is random and can be modeled by gamma distribution. This additional latency cannot be avoided when we use this blockchain applications and blockchain for the applications and services. So it is essential to design the blockchain-enabled network or systems by considering this ledger commitment latency. Especially for the real-time applications and services, this latency will be very critical. So when we bring this blockchain in those applications, especially we need to carefully design the blockchain network. And this blockchain and IoT and AI are the technologies that can be combined in multiple dimensions. So because the blockchain by using the blockchain technology, we can provide the trustness in the data in like IoT and so on. Also, it can provide the trust on the training model for the machine learning because they provide the trust in the data they use for the training of the certain machine learning applications. So however, when we use this disruptive blockchain technologies, we also need to think about the cost we need to pay. So this is the additional latency is definitely the one of the costs that we need to pay in here. So I want to emphasize about this latency issue in blockchain technology in this talk. And this is the end of my talk. And thank you for listening. Thank you.
Thank you so much, Associate Professor Lee, for that presentation on blockchain. And we have some questions for you right now as we go on to the Q&A segment. For those of you who are watching over there, do remember to type in your questions into the Q&A box or Q&A tab on the platform. And we've got quite a bit of time, so feel free to ask more questions. Now, first question that we have for you, Associate Professor Lee, is, besides the additional latency, what are the challenges of applying blockchain to IoT? Associate Professor, what do you think?
So besides the latency, I mean, I think there is also important issues that we need to consider. That is the load balancing. Actually, I didn't introduce the concept of a channel in this talk, but actually there are some concept of channels in the Hypertone Fabric. So in each channel, actually they manage the ledger separately. So, and then we also see that as we increase the transaction generation rate, which means the transaction generates very fast, then the latency increase very fast as well. So by this, we need to distribute this latency at the transactions over the multiple channels so that we can reduce the latency to commit to the blocks. So this load balancing will be one of the issues that we need to carefully consider in the blockchain design.
Thank you so much for answering that question. I hope that addresses the question from our audience. There is another question here that we have. It says, what kind of applications matter in the age of information? Associate Professor, what do you think?
Yes, so age of information is actually very important measurement, I think. This is actually a matter for all the applications that control the system based on the sensing data and so on. For example, in the autonomous driving case, when we do this, we need to have all the sensing information in the real time. And this accuracy of the sensing information is very important because when they can affect our action and decisions. So based on this, actually, it is very important to have the data, the fresh data, which has a low age of information. So I think we can develop some technology for those kind of system and applications. We need to consider this age of information concept, I think.
Thank you so much. We have a third question over here, and this time they're looking for a user case. So Associate Prof, they say, can you share a user case, if any, of blockchain technology used in federated learning for 5G in Korea? Do you have something like that?
Oh, this is actually a bit difficult question. But actually, I do not know any user cases that apply this blockchain for the federated learning. But I think we can definitely use it because in the federated learning case, we also need to share this learning model between the nodes. So to have the trust on this model, we need to use the blockchain technology, of course. Yeah.
Thank you so much. Let's see what is our next question. Next question is, a blockchain network itself needs to be monitored. Can this blockchain method be self-monitoring? What do you think?
Blockchain networks, yeah, so private blockchain network need to be monitored, and actually it's monitored by certain organization and authority. But actually, I cannot understand what the self-monitoring means here. But the private blockchain is need to be monitored by authority. Yes.
Okay, our next question, Associate Prof. Lee, is in your talk, you have shown the effect of blockchain parameters on the blockchain latency, such as the effects of block size, timeout, and the transaction generation rate, and so on. How can we use those results in real implementation of blockchain to lower latency? How can we do that?
Yes. So in this talk, actually, I want to emphasize the latency in blockchain design. So as I shown before, the block size and timeout, they affect the latency critically. So based on the applications and then the system that you wanted to bring this blockchain, you need to determine those parameters very carefully. And also, as I shown before, this transaction generation rate also affects the latency a lot. So as I explained before, we also need to use this result to distribute this transaction route to over the channels and so on.
Thank you so much. Now, we've still got quite a bit of time, so if you're watching over there, do feel free to drop in more questions into the Q&A tab. Our next question over here is there any study on the energy consumption impact if blockchain technology is widely used for all forms of commercial transactions?
Energy consumption, you mean?
That's right. Can we see that question again? Is there any study on the energy consumption impact if blockchain technology is widely used for all forms of commercial transactions? So is there any study on the energy consumption impact?
As I know, there is some work, but usually the energy consumption is matter for the public blockchain case. As I explained before, there are two types of blockchain, public and private. For public blockchain case, I think all of you know about the mining process, right? So anyone can mining and then can attach to the block for the transactions. So for this mining process, actually, we need to use all of the computation power and also energy and so on. So this is quite a matter. However, in a private blockchain case, actually this the ordering service is matching to the mining process in a public one. This ordering service requires very small computation only. Actually, what they do is they just collect all the transactions, enter the ordering service, and if the number of transactions become like block as much as the block size, then they generate the block. So this is very simple process. So for a private blockchain one, I think the energy consumption may not be that issue. Yeah.
Thank you so much for addressing those concerns, and we hope that addressed some of the concerns they have about energy consumption. Next question is, are there any blockchain-empowered cases in the manufacturing sector? What can you tell us?
Use cases in manufacturing sector.
That's right.
Manufacturing sector. That's
Not really.
It's a bit broad question. So, but manufacturing one, of course, I think blockchain can be applied in any places they need to manage the database and they require the integrity. So integrity means we need to make sure no one changes this data. So of course, I think applications in manufacturing sector, they require this. They can use this blockchain technology, of course. Yeah.
Great. Hopefully this next question will be something more specific. And the question is, which one do you think might be more promising in the applications of 6G? Private blockchain or public blockchain? What do you think?
As I actually, in my opinion, own opinion, I think private blockchain is more important. And I mean, the application of a private blockchain will be more various. So especially for the 6G as well, I think. So especially in the 6G, as I think the Tony also mentioned about the 6G requirements and the system and so on. But among them, actually one of the important thing is the machine learning based control and management in 6G. So to do that, actually we need to train this machine learning model, and the data is also very important. But if they use the different wrong data for the training, then it will be a big problem. So we can use this blockchain technology to manage the database and then provide the trust on the data they use in the training and so on. So I think the private blockchain will need to be really works do the more jobs in the 6G and so on.
And there you have your answer. It's private blockchain. Coming up next, we have another question over here, this time about telecommunications, and it's specific to Korea. It says, how active are Korean telcos adopting blockchain technology in their 5G architecture?
As I know, they are not specifically adopting this blockchain for 5G communication one. But as I know, they also developing certain applications that require the blockchain and so on. So I think not yet they apply this blockchain for the communication architecture and so on. Yeah.
Okay, let's see if we have any more questions. Do we have another one? That's it. Okay, we have finished all the questions from our audience. And with that, I want to thank Associate Professor Lee. Thank you so much for joining us from Korea with that empowering presentation on blockchain and for answering all those questions from our audience. Thank you so much.
Thank you. Thank you very much.